everyone, I am Adway Mitra, an assistant professor at Indian Institute of Technology Kharagpur, and today we are going to start with our new course on machine learning for earth system science. So, in this course we will basically have 5 modules. The first module will be on spatio-temporal statistics, the second module will be overview of relevant machine learning concepts, third module will be about earth system process understanding from data. In the fourth module we will try to consider the earth system observations using say the observations we obtain from remote sensing and so on. We will try to interpret them using machine learning and try to get useful information out of them. And in the fifth module we will consider like earth system modeling, which is something which many scientists in various domains like hydrology, climate science have been using in their own ways. We will see how those process based models can be improved using machine learning. So, we will start off with the first module on spatio-temporal statistics. So, this will basically give you the necessary toolbox to understand the and do the necessary computations with the kind of data which we will be handling in the domain of earth system sciences. The background which is expected for this course is that the students should be familiar with basic probability and statistics, like especially the concepts like say various probability distributions like the Gaussian distributions, gamma distributions, beta distributions, Dirichlet distributions and so on. Then the basic concepts like variance, covariance, conditional and joint distributions, expectations and so on. Like you are not expected to be greatly experts in statistics, but at least clear understanding of these basic concepts is absolutely necessary. The second expected background is that you should be familiar with the basic machine learning and data science concepts. Some of the more advanced concepts, say example those related to deep learning and so on, we will try to give a brush up or overview of those in the second module, but I would also expect that either you have already got the enough background knowledge of these topics, or you will be required to update yourself as the lectures proceed. Otherwise you may not be able to follow like the subsequent schedule modules like say module 3, module 4 and so on. Apart from that, it is also necessary to have interest in at least some domains of earth system sciences, be it climate or hydrology or say seismology or any other thing. Even remote sensing will do. But like at least some exposure to the, at least some domains of earth system science is a desirable criteria. And finally, you should be able to read and understand research papers, and there are very few standard textbooks and these kinds of things for this course, because this is largely a state of the art topic in which most of the reading materials will be from online sources only. So you should have the ability to search online sources and choose the relevant materials and learn them. And also as we move to the later modules, that is modules 3, 4 and 5, we will be dealing mostly with research papers, so which you will have to read and understand. So maybe not certainly not word by word details of research papers, but at least the by reading a paper you should be able to understand what the paper is about, what the aim is, what are the methodology used, and most importantly what data sources they have used, because in these kinds of subjects the data is like the most important thing. So now in this introductory lecture I will give you a template problem which might arise in this domain. So various problems which we will be dealing with, you can say is you can say this is a template for those problems. So the data which we will be handling in this course will be mostly spatio-temporal data. That means what? That means the measurement of something which is at a given location and a given time point. So, let us say that there are capital S locations in a particular region, and we are interested to measure a particular geophysical variable, which may be something like temperature, rainfall or something like that. Let us denote it by x, and that is measured at each of the capital S number of locations. So, these capital S locations, they can be either point or points on the in space, or they can be grid points. So, like as you know, the when we are studying any like art science related matter, like the standard is to divide the whole art surface into grids like of latitudes and longitudes, and so which divides the earth's surface into small square or rectangular regions. So, each of those regions can be called as a grid box. So, we either we can have like one the measurement at every grid box. So, which will mean that we are taking like there may be special variations within the grid box also, but we can consider its average value. Of course, that will make sense only if the grid box is small enough, otherwise we do not want to take an average over a region which has a high variance. So, we will so either we will consider that the earth surface or the region in consideration is divided into small grid boxes, at each of which we are reading the locations, or we can have what is known as in situ locations. That is something like we have placed a thermometer let us say on one particular building of IIT Kharagpur, and in that case we are measuring the temperature precisely at that point. So, when we are talking about measurement, special measurements, it can be either grid wise measurements or in situ measurements. Now, this geophysical variable x, which we are trying to measure, let us say we are taking its readings at regular intervals of time, which may be hourly, daily, like per minute, per second, or some kind of time frequency. So, let us denote these readings by x, s, dh. So, x denotes the variable, this superscript s, this denotes the location, and the subscripts dh, this denotes the time point. So, in this case d stands for day and h stands for hour. This is assuming that we are measuring the that variable at every hour of every day. Now, it need not be that kind of measurement, we may also be measuring that thing every year, every month and every day. So, in that case the we will index the variables like this as ymd. So, so basically the indexing depends on at what spatial and temporal frequency we are making the observations. So, this so this is the basic notation, like as for specific applications we will be changing it slightly to suit the needs. And also let us assume that these observations of these geophysical variables, that is we are able to observe it only at a subset of the locations and at a subset of the time points. That is, we do not have the complete observations of this set, but there may be only a certain number of locations where we have, let us say, the abilities to sense these or measure these geophysical variable, and further we may not be able to do it at all time points also within that period. There might be misses. There, like it is possible that from time to time that measuring system will be down and will not be able to measure it. So, such gaps also can be there in the data. Okay. So, this is the basic setting. So, just to illustrate it, so let us say that let us consider these time slices. So, t equal to 1, t equal to 2, t equal to 3, we are considering 3 time slices here, and these bubbles, these you can say are the spatial locations which we are talking about. So, like as I said, the spatial locations can be either in situ measurements, that is at specific points, or they can be over an uniform grid system. Now, as this suggests, this image suggests, here we are considering in situ measurements, because as you can understand that this is not like observations from an uniform grid. And these bubbles, as you can see, they are either blue or yellow. Now, blue means that is we have the observations in those locations, and this yellow or orange means that we do not have the observations. And you may also notice that at every point of time, t equal to 1, t equal to 2, t equal to 3, we never get any observations at these orange locations like S2, S9, etc. We that's because we do not have any sensing facilities in these locations. In the other remaining blue locations, we do have sensing facilities, though in some of the time points even they may be temporarily down or faulty or something. So, some of these blue some of these blue observations may be missing or unavailable at certain points of time, but these yellow or orange observations will never be available. So, now given this setting, what are the questions which we may ask, or what are the problems which we may be interested in answering? So, one obvious answer is that, so for like estimate the values of x at the yellow or orange locations where we have no observations. That is the first and rather obvious problem or question which we may ask. The second question is that is, can we predict the future values? So, we have, let us say we have observations at only the blue locations till a particular point of time. Let us say till t equal to 500 we have observations. Then in the subsequent time steps, what the observations are going to be at both the yellow and the blue locations, can we make a forecast of that? That is like the another kind of problems. Then the next set of problems are related to, are more diagnostic in nature. Like, can we have the observations at all the blue points, so can we identify some sort of spatial relationships between them? That is to say, can we say, for example, say things like whenever the observation in S1 goes up, that in S3 also goes up, while that in S13 goes down, or these kinds of relations shall we be able to identify. And the second related to that are like, can we identify some kind of trends or temporal behavior in the observations at the different locations, at the blue or the yellow locations. And finally, identify the anomalies or unusual events. So, there might be certain situations in which some of the observations at some locations have gone very high, or and persist to be like that for a few days. Now, this might happen for two kinds of reasons. Either the measurement itself has gone wrong, maybe the sensors which we are using, there is like some error in those sensors, etc., in which case it is giving faulty readings, or it might also happen that some unusual thing is actually happening there. So, if it is the first one, then the sensors need fixing. If it is the second one, then like it is a matter of concern. So, suppose we are dealing with gas sensors and we have a network of gas sensors and we are measuring the volumes of gases. Now, suppose the volumes of the sensors are giving high readings for some time, then in a particular region, that might indicate that a gas leak has taken place. Either it can mean that, or it can also mean that the sensors have gone wrong. But if it's like, if it is at only an isolated point, then it might suggest that it's a problem with that sensor itself. But if it is like including several sensors in a given in nearby locations, that it's very unlikely that all of them will be like behaving badly. So, most likely it is something urgent has happened there which needs our attention. So, that is the anomaly detection problem. Now, the mathematical tool which we will be dealing with for solving this problem is probabilistic modeling. So, these observation x, we will be treating them, or the variable x which we are dealing with, we will be treating it as kind of a random variable whose values are sometimes known and sometimes unknown. Say so for for the blue locations where we have the observations, or where we can measure the observations, we will just say that it's the values of the random variable are known, that is we have instances of that random variable. At the orange location we do not have them. Now, these like we can either consider each of them as separate random variables, that is the value of x, the measurement of x at each of these bubbles at each time point. Either we can consider all of them as separate random variables, which we will see in the next lecture is not very useful, or we can consider each of them as the realizations of the same random variables, or we can divide them into groups and just imagine that all the values in the same group are realizations of one random variable. And if that is what we are doing, then the question will be how to define such groups. So we will try to understand or address some of these questions in the next lecture, and then we will use the idea of probabilistic modeling. So what we already have is the data at certain locations and at certain time points. So now using that, we may try to estimate that is, we can actually try to build some kind of a probabilistic model using those random variables, assuming some kind of a relation between the different random variables, or trying to put in some other properties, or to capture their spatial and temporal variations and so on. Again, we will understand these in the next step. So if we are doing that, then we will there are some design choices which arises. So what sort of random variables are these going to be? We know that random variables can be continuous or discrete. Now that is, of course, we can decide like that based on the nature of the data. So if we are measuring something like, say, the amount of rainfall or the temperature, then obviously that's a continuous random variable. So we will be using some probability distribution which is suitable for these continuous random variables, so like, say, Gaussian distribution, gamma distribution, and so on. Similarly, if if the data is discrete, in that case we should be using some kind of discrete distributions, like maybe multinomial or categorical, or Bernoulli, Poisson, things like that. So so these are some of the design choices which we must make, and those choices which we will understand how to make them based on the nature and various properties of the data. And then whenever we are considering any probability distribution, it will also have its own parameters, like, say, the Gaussian distribution has the mean and variance parameters, the gamma distribution has the shape and scale parameters, the the Poisson distribution has the lambda parameter, which is the intensity, and so on. So how to estimate those parameters? So the answer is that we will have to estimate the parameters from the data, from the observations, by such parameter estimation techniques such as maximum likelihood estimate and so on. Okay. So maximum likelihood estimate we may not cover in this class, but like, you are expected to read up more about it from various sources. And here are some of the references which we will follow during this course. So we this first one, the Handbook of Spatial Statistics. This will be important for module 1. For module 2 and the subsequent module, you can consider this edited book, Deep Learning for Earth System Sciences. This is available, for Earth Sciences. This is available freely in online, and this is it contains like a huge bibliography of related research papers, and we will be going over those research papers especially for modules 3, 4 and 5, as and when the need arises. Okay. So with this we come to the end of this introductory lecture. We will continue again on the next lecture, where we will be understanding these spatio-temporal statistics in a bit more details. Thank you, everyone.